hello, people, right? Okay, what I'm doing is I'm recording my voice and everything that's written on here. And where's all that stuff going? You go to a YouTube channel, Chemistry with Dr. Smith. Okay? So you can Google Chemistry with Dr. Smith, or go to actually YouTube and things. But this is what you type in. And there's going to be a mess. Look at all of this stuff. So what you do is you clean up the mess by clicking on Playlists. And then you find your course, Chem 3421, Fall 2012. So you click on there. And this first one's removed because there's no sound. They haven't cleaned it up yet, but they will. So you take a look at this first one. Okay. So, all right. So here we go. So here it is. And if you wanted to see, this guy's voice is getting nauseating or whatever, you can skip to where are some problems, right? And once the whole thing loads, it would be faster. But you can skip to the problems and just scan through and see how problems were solved. And you can take a look at it on, on phone, computer, all that sort of thing. This isn't a very good example because there's nothing really big and long, but that's the point. And we kind of fast forwarded there, but if you let it load, it's a lot smoother, and you can scroll it along, and it just fills in as it goes along. Okay. So this is, it's not completely new, but it's relatively new in the educational world. And what they found, what they believe, and what I've kind of seen too through surveys, is that the most productive way to use this is a support tool. And it's doing what you're doing right now. You're sitting here and taking notes, doing your whole thing. But this is used as support. If you wanted to, how did he do that? Or it's before the exam, you want to review, or it's a support tool. And that's how it's been the most productive, not only for folks here at the lake, but nationwide for places that do this. Okay. That's about it. So you can obviously be anywhere. You missed class due to a sport, or you slept in, or you slept here, right? Instead of throwing spitballs at John, you can actually just go home and watch this. So make use of it. But really, your first line of defense should be your instructor, right? Chemistry with Dr. Smith. You can go to YouTube and type it in, or just go to Google and type it in. No spaces, Chemistry with Dr. Smith. And it'll pop up right there. And click Playlists, otherwise you have to dig for what you're looking for. You can also, I don't know if you're big on these YouTube channels, but you can subscribe. That way when I post it, it'll send you an email saying, hey, you just posted whatever. I should subscribe to myself to see what it looks like, but realize if you subscribe, you're going to get an email from General Chemistry too. But just delete that one. Okay. Lab. So if you look at our lab schedule tomorrow, we're on lab 2, and now we're supposed to perform check-in procedures and make solutions that we're going to use for the whole semester. One thing that we forgot to do, which probably is for the better, I just pulled out my book, Labs in the back. The very first sheet on the lab, right, after the yellow, is this calculator practice thing. So so make sure you bring this. We're going to do this first, and then we'll talk briefly about, how a lab report looks and that sort of thing. And then we'll make some solutions. Let's see, kind of flip in. Oh, here's a check-in page, right? Just look through your cabinet and make sure what you have, what's there is there. It's really not that big a deal. You're doing the lab and you need it, you go get it anyway. But it might save you some time if you have everything there. So you'll do that. And then you flip over to the next page, and there's some directions to solutions. But all the directions aren't there, so you really need to bring your book. Okay, because the book actually has, if you get stuck making one of the indicators, bromocresol green, well, you're going to need the book because it tells you the directions. I guess you could Google it too. But. Okay, but it'd be cleanest and quickest if you bring your book. Okay, so we're going to do the calculator practice sheet, talk about how to make a lab write-up, check in quick, make solutions. Can that be done in 2 hours? Is what's been going through my head. Because the advantage is you start at 9, and I don't really have a good feeling for this. Well, we have till 12? Oh my goodness. Well, then shoot. 9 a.m., right? We go to 12. I forgot about that.
So you think it's only going to take 2 hours from like 9?
Oh, that's what I'm questioning. Because I know some folks have to leave at 11. But we're going to be pretty much done by then.
Okay.
I would think. I mean, how considered really to do? Especially if you make your solution, you run away. Right?
We're going to make all those, or we're going to get...
No, everyone, you get stuck making something with some partners.
Okay, good.
Right? And so, yeah, I'm glad you brought that up, that some folks have to leave a little bit early. But they still have... All right, we're doing a real lab. We'll start at 8, then there won't be any worries. But, okay. So 9 a.m. tomorrow is lab. Papers, I'm usually a lot better about returning these quicker. I'll get these back like the following class period. Finally got the folders put together, so next class period you'll start getting all this stuff back. Okay. And where are we now? We're talking about tools of chemistry and sig figs. And 63% of all wrongful convictions are due to screw-ups. All right, and I'm sure we're going to be talking about some of them, especially with the pipetting and things. At least that's what they say. I don't know. Okay. Some safety highlights. Natalie, what is the problem with the first one? What's the big deal with contact lenses? Natalie.
Natalie, right?
Yeah, Natalie.
Okay.
What's the problem?
I guess fumes, right? I was told that fumes can, like, get stuck to your contact lenses and, like, stay in your eye.
Yeah. So anything that dissolves in water, right, can dissolve in your eye. Contact lens covers what, right, just dissolves in your eye, it gets under there, it gets worse. So you can run over to the little hose thing and spray all you want, it's just going to keep burning. All right. So you can't wear contact lenses, even under the glasses, because nothing is airtight. You wouldn't want to wear airtight, man, that'd be uncomfortable. So you can't wear contact lenses at any time. We'll talk more about safety and lab, but that's a big one. Chemical hazard labels. I didn't bring any chemicals in here. They're all smelly anyway. Just leave them where they're at. The ones that are harmful. The numbers in those boxes, they go from what to what? Kimberly, they go from what to what? Oh no, the number. They're going to put a number in each box. Is it 1? Don't they start with 0? I think in the book, don't they? 0 up to 0 to 4? Okay. 0 to 4. So 0 you think is good or bad? I mean, well, high degree or low degree with these different categories. 0 is, no effect. So what are these categories? Adrian, blue, red, or yellow? What's one of these categories? Anyone help them out? It's right there. Go ahead.
Red is fire hazard.
Red is fired. Now, usually they don't say fire. They say flammable. All right. Blue? Cat, keep going. What's blue?
Blue is instability.
No, blue's not instability.
Oh, sorry. It's color blue, but it's yellow. Blue is health.
Health. That's okay. And yellow is instability. Yeah. So why, now that she's got them all covered, what's the purpose of the white box then? What's that? Yeah, it's just whatever special note would make sense. You could write acid in there, base. Maybe don't store with this. Store under nitrogen, right? Yeah, I think special instruction kind of thing. So, and all those numbers go from 0 to 4, except you're not going to have a number in the white box because that's just special instructions. And it would be nice if every manufacturer would do this, right? Because then you could have all these chemicals you just bought, and everything that has a 4 in flammables, well, you'd want to keep them all together, right? And keep them all in this flammable container. It'd be so much easier. But they all don't follow this. But so it'd be nice if they did. What would an example of the health problem be? Kat, what would be an example of a health problem? I'm thinking like something that causes cancer. It's called a carcinogen, right? And then there's other stuff that affects other things. You biologists have words for all that stuff. Okay. Instability. Just instability. Something's not stable. This chemical's not stable. Whoa. It could explode. Exactly. It's going to build up what inside there? Pressure. Pressure. It's going to build up pressure. So something's decomposing, and it's building up pressure, and it's going to go boom. That's exactly what's going to happen. Okay. Okay, we got the colors, we got the numbers. Why would technique be important in a forensic science lab? Well, it's kind of obvious, right? Research lab, same story, except it's results. I guess research lab, it's more of a philosophical point of view because scientist says something. Other scientists understand, yeah, you know, that's what they think according to everything up to this point. Other people take it as, you know, it's like written in stone, man. That's fact. You know, no, right? So you got to be kind of careful. Analytical balance. Okay, let's demonstrate it. How would we mass something out here? Okay. So the problem is I need to mass out some sodium chloride. So I take some of this stuff. What is this stuff? What is it? Whey paper, wax paper, right? Nice and shiny. And it's nice because it's really hard to get fingerprints and stuff on there. But even if you did, we're going to push the tear button anyway, so we don't care. And instead of putting it in there like this, how are you going to get the salt out of there and pour it in, I don't know, pour it in here? Yeah, I have to fold. So it might be easier to fold it in half first. That's what I'm driving at. Fold it in half first, and then put it in. So, and no one wants to do extra math, so you push the tear button first. Push the tear button. Oh, it's not even on. Well, let's get that off of there. All right. Now let's push the tear button. Why? What's the big deal with all these glass things around here? Wind. Because it's 0.0002 gram. That's where it's bouncing around. So, right, it's always. Poor Danielle's gonna be sitting there forever. She doesn't close the door. So close the door. Another thing that helps is when you're gonna add the salt, line this up with the paper, because then you can sit there and tap the spatula on the glass to get the mass to fall in that you want. I should have got a bigger one of these spatula honkers things, right? But usually you don't want all that. All right, so you just sit there and you tap it, and you're watching that thing as you're tapping it. All right, so they can get what you want. See what I'm saying? It's a lot easier. Let's say that's what you wanted. Close it up. And then, John, what does it say? Well, this is like 12 grand, man. Give me all the digits. All the digits that it says. 0.0800. 0.0800. Okay, yeah, write down all those digits. Are these actual zeros? In other words, are they significant? Is that actually 0? Yeah, because we could keep dumping in some more and change it. It might go up to 1, 2, 2, 3, right? So these are 0. Those are significant. And we're going to get to this, but that one's not. Placeholder, yeah. Okay. Well, there's a trick to knowing what's significant and what's not, and I'll show you in a little bit. But you drag it out of there, fold it up. That's why you put it in half first. So now you can walk back to wherever you had to walk to, right? Because your stuff is probably halfway across the hallway. And all of our balances they are. You got to walk outside the lab to even get there. So, and then you get to your little place where you want to dump the stuff. All right. Now, anal lab is anal. Did we get it all out of there? This is solid slide's really nice. So odds are we probably did. But you're going to be massing stuff that's really chalky, like calcium carbonate. Oh, I don't have my little... Well, I guess I'll have to use this. And my little doohickey, this thing. All right. Put it on there and just run it in. All right? So everything you massed out is in there. This lab is anal. It really is. I dribbled some on the outside. Who cares if it's just pure water. The problem is I want all the salt I massed, all 0.08 grams, 0.08000 in here. Right? Want it all in there. All right. Then you throw that away. Fill it up. Now remember, what is this flask called? Volumetric. All right. So again, if I spill water here, it's no big deal. The thing I don't want to screw up on is going over the line. All right? And before I do go up to that line, I should probably make sure it's all the D word. Dissolved. All right? And then when I start getting close, I might not stop. And then when I want to get it right on that line, what's that? Error called, or the P. All right, because I want to look at this so I see one line going across. Right? Hold it too low, I see 2 lines. I see 2 lines. See 1 right there. Parallax error, right? Now, what's the name of the bottom of that little meniscus? You want that right on that line. Parallax error is where you see more than 1 line, right? So if you hold it too low, you see actually 2 lines.
I just didn't know there was a name for it.
Yeah. Okay, and then now it's not quite mixed yet, so we should have a stopper. But how many times should you do this? How many times should you do this so that it's mixed? Assume it was all dissolved. How many times do you think you need to do it? Someone actually studied this. It's 12. 12. That's what they say. But could you tell? I doubt it, right? Okay, anyway, that's the idea. Okay. Oh, there's one thing we forgot to do before we even did this. Now, how do you know this thing, how do you know the 0.08 grams is 0.08 grams? This thing had to be, what's the C word? Calibrated. Okay. Now this balance is only like 8,000. So it comes with its own calibration weight. Let's see if this is calibrated. All right. I'm going to put it on there. Tear it. Go ahead and tear it, John. Okay. So Danielle, this reads, now why am I not wanting to touch it? Yeah, I'll change its mass. Okay, that's how many grams? 100. Okay. So let's tell me, it's on 0 now, right? Okay. Is this dude calibrated? No, he's not. He's close. 99. What did you say? Say it louder.
99.9983.
Yeah. So I mean, he could be better, right? But he's pretty close. So we should probably push the cal button and fix all that. Okay. Anyway, so I should probably do that for our balances. The nice ones that we're going to be using, they have internal calibration. Every once in a while, you're in there, you hear this. It's doing this internal calibration. So kind of nice. You don't have to mess with it. So that's 2 ways to calibrate it: internal and external. Okay. Buoyancy. Miriam, what's buoyancy? You ever heard that word used anywhere? Buoyancy? Buoy? Yeah. I like the word that she was starting to use. Do you hear? The pressure. Right? When something exerts a pressure on something else, she changed herself. And it was just force. Pressure is force per unit area. Same thing. But I like the idea of pressure. To me, my brain just visualizes pressure more. Because pressure I see is more spread around. Force, I feel it more like this. That's how my brain works. But yeah, you put this guy on water and he floats, right? He's buoyant. Okay, so the water is exerting a pressure on the disposable pipette. Disposable pipette's pushing back with its pressure, but they're definitely not, right? They're definitely not equal. Because if they were equal, this thing would be pretty much where? Just floating in the middle somewhere. Or you could position it wherever you wanted. You could position it in the middle and it would stay there. Position it on the bottom, it would stay there. Position it on the top, it would stay there, right? They're the same density, right? So things that have different density, something's going to be buoyant. Okay. When does buoyancy err? Oh, what's an example of buoyancy? What's that? Straw? Yeah, dump a straw in water, it floats. It's buoyant. Right? Boats, whatever. Okay. Ice cubes. When does buoyancy error occur with a mass balance? What the heck? Buoyancy error with a mass balance? Remember what we did? Folded our paper, teared it, put it, all right? I mean, anything you're going to mass. How can there be buoyancy error? Well, that's pretty good. I mean, there's no wind blowing in there. Up or down, so it's not, that wouldn't be quite buoyancy anyway, it's kind of like blowing on something. How can this be buoyant? What is it in? If something, for something to be buoyant, it needs to be in something. It's definitely not in water. What is it in? It's in air. It's in air. You're in air. I'm in air. This thing is in air. So things could be buoyant. Now what? Let's see how this works. I think it might be easier for me just to show you. Okay. I want to mass this. I'm going to mass it like this. All right, I'll mass it like this. Well, the problem is I want to find the mass of an empty syringe. So here's one way to find the mass of an empty syringe. Oh, I better keep that on. Okay, now, Jeff, you got to help me here. I'm going to pull this down, and then you're going to stick the nail in there. In the hole. See that?
Right there?
The one above it. There you go. Whoop. Let's get it up. I guess it would have worked. I was just trying to make it look nicer, so the end is over here. See how hard I'm pulling? Why do I have to pull so hard? vacuum. Yeah, there's nothing in there. There's nothing in that syringe. Whoa. Oh, not so far.
Right there.
There you go. And there. All right. There's the other way. All right. It's the same. There's nothing in there. It's a vacuum. That's why it's pulling so hard. So here's two empty syringes. Should they both have the same mass? Yeah. Right. They're two empty syringes. Let's find out. Okay. Does it say 0, John?
Yeah.
All right. So since this is all done, let's just do this one first. Okay. What does he say? What does it say?
80.1030.
Okay, that's the funky way of the syringe with the nail in it. Okay, now let's let them out. Now find the mass with this guy and put the nail on there. Now what does it say? Very different. One of those is right, one of those is wrong. The problem is where is this coming from? I'm working at, you remember your general chemistry labs? Probably a lot of labs. You read the directions, and then you gotta just do the step by step by step. It's so boring, right? That's pretty much why I have you guys come into lab when you have questions, because it's so boring for me to sit there and I do nothing. So I'm working on this whole new pile of labs, and one of them has a mass. It's an ideal gas law, so I need them to mass. They're gonna stick this in a bag with oxygen, fill it up with the oxygen, right? Cap it, right? I need to know the mass of the oxygen. They're going to play with the ideal gas law, because look how easy it is to measure volume and things and temperature. That's all they're going to play with. But if you want to measure the mass of the oxygen, you have to subtract out the mass of the empty syringe, right? So I'm playing with this. I can't get the right answer, can't get the right answer, can't get the right answer. Because I was measuring the mass of the empty syringe the way a typical normal person would measure the mass of an empty syringe, right? But that's not what I found the mass of. I found the mass of this guy filled with oxygen. What changed big time? And it has something to do with density. What changed big time? Not really mass, because it's just oxygen, it's gas, it's really light. I mean, you can mass it, and you can, but it's really small.
Pressure that was
What's the volume? Density is mass over volume. So I just measured two objects, supposed to be pretty much the same thing, but the density is hugely different. So if I want to measure the density of an empty syringe, I have to do it this way, because the other object I'm massing is, all right, this guy filled with oxygen. He's this height, right? So the volume will be the same. So that way the density is somewhat close. So the buoyancy is pretty much the same. You can't stop buoyancy. It's always there. The only way to stop buoyancy is to suck all the air out of this thing and do everything in a vacuum. That's the only way to stop buoyancy. So in other words, if you want to measure two things and not have any buoyancy air, the density's got to be the same. Okay? And that's a problem with measuring hot objects. You'll get close to the right answer, but its volume's a little bit different. And there's convection problems going on too. So you can't stop buoyancy air. The only way you can is to do it in a vacuum. Okay? You want to measure things with the same density. Or at least as close as you can get. Volumetric glassware. Oh, we already did this, right? We dumped in, we lost the number, 0.08 grams of sodium chloride. Here it is. We dumped in 0.08 grams of sodium chloride. In this flask, which is 100 mils, well, how would you get the concentration of this stuff? Well, so you can label it, write big M, sodium chloride. Use molar mass of NaCl. So divide the 0.08 by, I don't know, so 23 plus 35, that's about 58, 58.45. So 0.08 over 55.45. However many moles that is. Where's that? Calculator. Right, 0.08 divided by 55.45. It's about 1.44 times 10 to the negative 3. And that's what a unit? Moles. Divide that by what? To get big M. Yeah, it has to be liters though. 0.1 liters. Move it over 3 places. 0.1 liters. And that I can label my big M. Divided by 0.1, 0.014. So that's what I can label my sodium chloride solution. 0.014 big M sodium chloride. All right. You kind of jumped ahead a little bit, but that's okay. Yeah, it was right here. Why are, which one? Which one you're not supposed to, Casey, which one are you not supposed to put in glassware? Casey, which one? 1 in 3 chance here. Acids? No. It's bases. Why bases? What's that? No. Why bases? Bases actually start etching away at glass. So that's the problem. You'll kind of destroy your glassware but more importantly, your base concentration isn't going to be what you thought it was. So that's why you can't put bases in glassware. So when you're making your base in lab, make sure you put it in plastic. What is the tolerance of a 100 ml volumetric flask? What's meant by tolerance? Jamesa, what's meant by tolerance? Tolerance. Where is she? Where is she? Jamesa, what's meant by tolerance? Somebody help her? What is tolerance? What's that? Yeah, because some volume of this container, right? And the tolerance is, well, it can hold 100 mils, but that's not the tolerance. Oh, here's a hint. Can you read that little thing? Yeah. There it is. Plus or minus 0.16 ml. Now, not all volumetric flasks that are size 100 mils have a tolerance of 0.16 mLs, but this one does. So when you write down the, oh, how much did you take? Or what's the volume of this thing? You should really technically write 100 mils plus or minus 0.16 mils. This is the tolerance. Okay. It's the error. I think a better term and a more healthy term than error is standard deviation. Because standard deviation is something where you do something again and again and again and again and again. What's the variation? How much did it vary? That's standard deviation. So if you use this thing again, 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 and again, and again, right? What's the variation between all these different 100? Because they're supposed to be 100 mils every time. But if they vary by about 0.16 mils across the board. Standard deviation. It kind of makes more sense than error, but technically you're right. It's error. Okay.
So then we go with what is on the flask?
Yeah.
The little table?
Well, I don't know. You have to go on what's on the flask. There's all these different manufacturers, right? okay, I have 100 mils now, well, plus or minus 0.16 mils, of 0.014 molar sodium chloride. Danielle needs to drink this for some reason, but she needs exactly 100 mils. Can I use this? You know, just gurgle, gurgle, gurgle. That's the question. Can this be used to deliver 100 mils with that same tolerance? So that means she's going to drink it and get 100 mils plus or minus 0.16 mils. Why not? You're right, you can't. Because, I don't know, she's guzzling it, guzzling it, guzzling it, guzzling it, right? Yeah, there's still stuff left in there. That's the problem. Right? So you can't. Can't use this to get 100 mils. Can't use these volumetric glasses to get any volume. Remember, anal lab, man. Don't do it. It'll cost you on your lab. Okay. How would I know? Let's back up a little bit. How would I know that you weren't too anal about measuring this volume at this particular step in this lab? How would I know? Am I sitting there watching? No. Yeah, almost all these labs, everyone individually has their own unknown. If you get the wrong answer, I don't know why you didn't get the wrong answer. Sometimes I can tell in the calculation, but I don't know. It could be so many different things can go wrong. So that's one of them, right? Okay. So definitely no. Using the mass sodium chloride, what will the concentration? Oh, we already did this one. Will the concentration of sodium chloride equal? We said it was 0.014 molar. All right, we skipped. We should have waited to do that. And how would you prepare it? Well, you kind of saw me, right? Mass it out, dump it in there, dissolve it, fill it up to the mark. Oh, do you recognize this? The brackets means concentration. Glass, okay, so you actually want to deliver some solutions. You actually want to deliver a known volume. A 50 ml pipette. I couldn't find one. I didn't really look too hard because I found this one. So let's just change this to 25. Okay. Erica, what is the tolerance of this thing? It should be up here somewhere. 0.03. This guy. He's a Fisher brand. I don't know. But, okay. Hey, Pedro. So, it just depends on which one you grab, what the manufacturer is. You kind of look at it. Okay. So this is what you'd use to deliver it. Do you remember how to use these things? Oh, they were not fun at all. Remember this? All right. Maybe you got good at it. I don't know. But it took forever. All right. Now, maybe this is your base or your acid. They want 25 mils. Now, what's the word they use? A real hint. When you're supposed to use this, it starts with an A. It starts with an A. Aliquot. Give a 25 milliliter aliquot of this solution. That means pipette every single time. Can't use graduated cylinders. Can't use beakers. No. You have to pipette it. But you got to do it right. So first get all the air out of the bulb. I don't know, and I guess pick your favorite connector there. There's little BBs in a tube. Could have squeezed this one too. Jam it on the end. Stick it in there. Don't put it on the bottom because then it's hard for it to suck, but I guess it'll still work. And you bring it up. All right? Now, if you're really handy using this bulb, you can use it to deliver the 25, but I'm not very handy with it. I like to go way above it. All right? I don't know if you can see it, but I went way up here. That way I can take it to wherever I need to go, right? Pop this thing off, and then I just use my thumb. Because this thing, I don't know, you can use that, I think it's the E button, the exit, but I don't know, I can never get him to stop right on that line. I don't know. I mean, if you can, that's great, but so, and then you put it back over the solution, and don't remember that parallax thing. So you see one line, and slowly just release your thumb. You can put that thumb back on. release, back on, until you finally get it. There. Okay, now you take it to wherever you need to go, all right, and then you dispense. Now there's supposed to be stuff left in there, right, especially on this tip. I think that's supposed to be there. That's right. You remember doing that? Okay, so that's how you get your 25 mils. I better set them down. Okay. Solids. Now we talked about meniscus and parallax, the barrette. All right. Do you have to spend a lot? You're going to do a titration. That means you have to, you're going to rotate this guy, you're going to dump some in here, and you stop when it changes color. So you have to record final minus initial on here. Do you have to spend a lot of time to get it right on 0? Does it make sense? I mean, it's kind of helpful if you do, because then you just record this last number. There's only one number to write down. But I would rather just dump it in somewhere, fill it up, who cares, right? Write down the initial, and then you start right away. Then just whatever you get, final minus initial. It's kind of fast. To me, it's faster, but it's up to you. Okay. But make sure when you read these, again, watch that parallax problem. Bringing a solid to constant mass. Oh, hang on. Let's back up a little bit. We've got to be anal with this. Let's hand this to somebody. See if... I'll write down what I get behind the screen there. See if Joe gets the same thing here. Average Joe. Okay. Hang on, these bubbles. Oh, remember too when you're doing this, filling this thing up, what you're supposed to do? Yeah, fill him up too, right? Okay. Come on, bubble. All right. Okay. Okay. What do you get? And then we'll raise the screen. Wow. Good job, right? See, that's what you got to do. You got to read between the lines. That's what she did. She guesstimated. Great. Very good. I didn't think that was going to work. Okay. Very good. Oh, no, because most everybody, right? You just, okay. She put some effort into that. That's good. Okay. What is meant by bringing a solid to constant mass? Danielle, what's meant by bringing a solid to constant mass? You're going to have to do this in lab. You're collecting this precipitate, and you got to bring its mass to constant mass. Does that make sense? Yeah. Bring it to constant mass. It's all wet, it's precipitate. What does that mean? Yeah. Like this precipitate idea. What's the problem? There's also, it's wet. So you dry it. And then you gotta let it cool down because buoyancy, right? And then you put it on the balance. Is it completely dry? Can't tell by looking at it. So you got to go back to the oven, right? Let it dry. Bring it back. Cool down, right? And when you get the constant mass, you know it's as good as it's going to get. Has to be right. So that's what they mean. You can't get the mass any lower. Microwave oven. Yeah, it's for drying. It's a lot faster. Except it's a lot easier to steal. That's why we don't have one anymore. I had a big one. Someone just walked out with it. So now we're stuck with using the old-fashioned hot ovens. But Hmm? Okay. What time is it? Oh my gosh, why'd you guys stop me? I didn't even know what time it was. I'll finish that on